Okay, hello everybody, and welcome to the first live stream of 2019. This is our first Astro Coffee Hangout for what I think has been a really busy year already. I can't believe it's only like the 10th, because already we've had a spacecraft go in orbit around an asteroid. We've had New Horizons fly by Ultima Thule. We've had a solar eclipse. We're about to have a lunar eclipse. The AAS meeting, which we're going to talk about today, is going on this week. So it's like, wow, talk about a busy year, and it's only January 10th. And so anyway, welcome to 2019. My name is Tony Darnell from deepastronomy.space, and we are talking with our Astro Coffee Hangout. And today it is just me and my good friend, Dr. Carol Christian from the Center for Emerging Media. Hi, Carol. Happy New Year.
Hello.
I'm so glad to see you again. Now, today, what we're going to do, since this is a big week in the astronomical community, and Carol just got back from that meeting, we're going to talk about something that everybody's calling the Superbowl of Astronomy. And I guess it kind of is, right, Carol? I mean, is there a bigger conference for astronomy? Maybe the IAU.
The IAU, but I think this one is pretty concentrated on science results and also technology. The only thing I don't like about the Super Bowl is that there's no winners and losers. Nobody comes away with the cup and other people lose. I mean, everybody's a winner. It's like all kinds of science that's being done, and also technology and things about the new telescopes that we're thinking about. So it's pretty exciting. And you get to see your friends who you haven't seen for a year.
That's right. So. That's exactly right. Okay, hang on. Okay, so hang on just a sec. Larry Keesh, you're commenting there's a bad echo, but John Suffel is saying, I don't hear any echo. And Sure Shot says, I don't either. Okay, that's 2 against 1, so I'm saying there is no bad echo. Larry, you might want to make sure you've got some windows closed. That's the thing I always have a problem with. All right, well, I guess the big news is, let's just get this out of the way first. We all know about the government shutdown. We invited Harley Thronson, our colleague at NASA, to join us to talk a little bit about this, but there's a partial government shutdown. NASA employees are not able to do a lot of things, but they are able to do a lot of other things, and this doesn't really affect the Institute, does it, Carol?
No. So a lot of the work that's done for National Science Foundation and NASA, as well as many other federal agencies, is that there's a whole cadre of people who are civil servants paid directly by the government. But when you have a specific expertise, there are contractors that provide that expertise. So like launching satellites and building rockets and stuff like that. Those are not NASA employees. And in particular, I want to harken back to an old report not a million years ago, but 40 years ago or something like that, the Horning report, which actually talked about why there should be science institutes. And the idea was that scientists and engineers and the support staff should be in an institute which is adjacent to or part of an academic institution, but as a research institute, providing the expertise related to whatever their activity is. And that idea was specifically for astronomy and astrophysics, but it holds over to, any kind of science discipline where you have an institute of scientists who are researchers active in the field, as well as engineers, and they provide the scientific and technical support for a facility that is offered to the entire community. And part of it is, the same idea was at Canada, France, where I was a while ago, that, you could have a skeleton crew run the telescope, but unless you have researchers there who are trying to use the instrumentation, not only testing the instrumentation, but using it, and their research depends on it, then you can bet that those instruments are going to work. And the scientists are going to speak up and say, we need this and this and this. And in addition, I think we've shown across astronomy, and in particular for Hubble Space Telescope, as well as the other ground-based and space-based telescopes, that when you do research with an instrument, you also develop software techniques that enhance the data. Your calibrations are robust, all that kind of stuff. And in our case, we have this great archive, which is also has science advisors. So that whole idea is really important. But those are not civil servants. We all belong to some corporation. So in our case, it's the Association for Research in Astronomy, Association of Universities for Research in Astronomy, or ARA. And there are there are something like 40 universities who belong to it. It's partially NSF funded, partially NASA funded. And so we work for that nonprofit corporation, and that nonprofit was specifically founded to do education and research and run facilities for the country.
So that kind of insulates these programs from any kind of big disruptions like a government shutdown then, because you still have people from all over different organizations involved working on things and managing the data pipelines and things and the observations and things like that. Like
exactly. And you can't be starting and stopping work. You shouldn't be starting and stopping work anyway, even the government people.
I know.
But the idea was, to a certain extent, you can't just stop operations because, people in politics think that they need to stop the funding flow. So in general, there are contracts to the contractors. That's what they're called, contractors. And so those contracts, are signed by the government, and they will provide the money for those contracts for a specified period of time. Now, it can't go on for years, but it can go on for a period of time, and that allows us to have continuity. So we're operating, Hubble, other telescopes are operating. In some cases, there might be like pipeline handling of data or something like that, which is handled at one of the centers, and maybe that's not happening. But for Hubble, that's happening. As far as I know, for the great observatories, that's happening too. I mean, I talked to the people from Chandra and Spitzer, and the contractors were there, the scientists were there, and data's coming in and being archived and used, and research being done. So I would say, actually, at the meeting, and we can talk a little bit about the format of the meeting, but at the meeting, I have to say, the contractors were running everything. We missed our colleagues, but we were able to handle everything else that usually goes on.
Yeah. So in the context of our discussion today, since we're going to go through some highlights that you noticed from the AAS meeting, the winter meeting that's going on, or I guess it ended today.
It just ended today.
Yeah, it just ended today. Did you notice a big difference with NASA personnel? I mean, I think the estimate was that about 15% or so of the registered participants couldn't make it.
Certainly had an impact. Unfortunately, had an financial impact on the professional society. Now, we don't see that directly, but that will hit us in the long term.
You mean the AAS itself?
Yes.
Yeah.
But I would say, yes, we noticed that not everybody was there in the day. So let me describe how this meeting is run.
Okay.
So in general, there's everybody registered, and then there's a big area at a convention center, which is for exhibits. So there's a lot of exhibit space by universities. The AAS itself has an exhibit space. National Science Foundation, NASA, Space Telescope, Chandra. Telescopes that exist now, telescopes that will exist in the future. We all have booths where we hand out information. There are people who build instruments. There are the big companies like Northrop and Ball who are there. So there's a lot of exhibit space. There are the publishers like Cambridge University Press that published our book. Jean-René Roy and myself and Pierre Villiers' book. So there's that kind of stuff. There's even a little tiny booth that has jewelry. so there's a lot of stuff. There's a place for people to sit and chat and get food and that kind of thing. So that's the big main conference center exhibit space. And then elsewhere, there's a large area, which is usually something like a ballroom, which can be segmented. But for the plenaries and the big part of the meeting where everybody goes, it's one big room, and then it can be subdivided into smaller groups. And then there are smaller conference rooms around the conference center for the topical discussions. So there are sessions on galaxies, there are sessions on star formation, exoplanets, solar system. There are also all of our committees that meet that are planning strategies for the future on the telescopes that we're going to be building, what people want to do with them, giving information to the community. So all that stuff is going on. And in fact, the schedule is so packed. It goes from 8 in the morning till 8 or 9 at night. And there are parallel sessions, so you have to judiciously plan your calendar every day on exactly what you're going to do.
I know. I can't tell you how many times when I've gone, I've had to choose between one talk or another.
You have to, and if the chair of a session keeps everything on time because the times are published, you can actually squeeze in from running from room to room. But if somebody talks over or something like that, you might miss a talk. The other thing is that NASA brings something called the Hyperwall, and this was we were discussing whether they were going to bring it or not because it's called the NASA Hyperwall, but in fact that is owned by a contractor, and the contractor brings it and the contractor runs it. So I gave a Hyperwall talk, and the Hyperwall was there, and then there were people also handing out literature about existing observatories as well as observatories of the future like WFIRST and.
Oh, that must have been really cool. Let me just give people a sense of what you're talking about there. Larry Keese is talking about going to these AAS meetings maybe in the future. And so he's like, do you have to be a member to go? Do you, can you just show up? That's right. You can get press passes. You can also get a registration for non-members. So you can go. You don't have to be a member of the AAS to go. But there's this thing called a Hyperwall, which is this giant, I don't know, how big is it, Carol, physically? It's like...
It's like a bunch of large screen TVs. I guess it's 9 by 9, 3 by 3. So it's
huge by enormous. It's really high resolution screen.
Right. It's high resolution, and so you have to modify your normal PowerPoint or whatever, Keynote, whatever you PDF, whatever you use for presentation. You have to modify it and export everything in very high resolution. So I did a talk on the Servicing Mission 1. Science seminar that we had in December that I organized to talk about all the science that had been done since Servicing Mission 1 and how it was that Servicing Mission 1, which is the one that provided some new optics and paved the way for new optics being incorporated in every instrument to restore Hubble to its intended performance, talking about all the science that's been done since that time. So covered everything, solar system, acceleration of the universe, all that stuff. So there were talks about all that kind of stuff.
I love how you're like, acceleration of the universe, all that crap.
All that stuff. So the Hyperwall was there, and in general, because, and now, astronomy efforts, both technical and research, are done by large teams. So if somebody like Harley can't go, his collaborators might be at a university and they can give the talk. And so in general, that's frowned upon. But in this circumstance, if somebody couldn't make it to the meeting, then a collaborator could give the talk. So usually there were a few talks that were just like totally canceled because a civil servant somebody from NASA or NSF wasn't there. The one big thing, which was unfortunate, was they canceled the JWST town hall, which...
That's right. I heard that.
This is like off the record, not related to my employment, but I felt that the Space Telescope could have conducted that town hall.
Sure. Because if you don't know, the Institute...
We know all the science stuff. We would have just said, look, we're not going to talk about the policy or the budget because we're not in charge of that. So there would have been maybe one segment of the town hall that wouldn't have been discussed, but we could have discussed everything else, the science capability, what we're looking forward to, how do the instruments work, all that kind of stuff. We could have done it, but they just decided to cancel it. NASA decided.
Right. And so for background...
Today, we had our Hubble town hall, And the Institute had its town hall, and the other observatories had their town hall. So I don't know why JWST canceled.
Well, so for background, let me just say that when at every one of these meetings, NASA does several town halls. They call them town halls, and they do one for they do one for JWST every year, and they do one for Hubble every year. And what they essentially are is an update on the status of the mission, what's been done, where it's going, and the plans, and any things like that. And those are really big events because they usually give it in the biggest auditorium, so that because everybody's interested in these really big projects. So maybe now maybe Carol, you were asking why didn't they do the JWST one? Is it because that the Space Telescope Science Institute did the Hubble one? Is the reason that NASA didn't do a JWST one, do you think, because the handoff hasn't happened yet? There's kind of a ownership issue with the project.
No, because there are people from our institute that are involved in the calibration and the integration and all that. We're involved in every.
So you're saying that could have happened.
Yes, we could have done it, and we have pictures and all that stuff. So all of that could have happened. There's one segment of it where the program officer from headquarters does give an overview of this is where NASA thinks this observatory is and addresses the funding thing, but that's only one talk.
Yeah.
So we could have said, you know what, we'll have a discussion instead, and we won't talk about that. We'll talk about all the instruments because we're involved in the instrument building and the instrument integration.
Yeah,
so I think we could have done it.
Oh, well.
Anyway,
right.
Be that as it may, all the other town halls, which NASA is involved in as well, took place, like WFIRST and all that. They all happen.
Carol, what is going on with WFIRST? And I really want to know, what is it still going? Is there any danger to the project?
We have funding for the year. I can't answer what's going to happen in 2020, but we have funding now.
And that funding is for design still?
The studies and the design and some technology development, yes.
Okay. So WFIRST is still alive.
Yes.
It seems like it's going year to year on its funding. What do you have a personal opinion about whether this is going to fly or not? Or do you not want to say? I understand if you don't want to comment.
I'm not that knowledgeable about it. I think the hang up is not the will of the scientists or engineers. I think it's the will of NASA they're nervous. They want to make sure, they want to make sure JWST gets up there and launches. And, people made, the problem is that we live in this, it used to be 144 characters. Somebody can make some offhand remark about, if they can't launch JWST, why should that a WFIRST? And somebody hears that who doesn't know anything about it and says, okay, we're going to look into this.
I know.
So sorry, we all think it's a great observatory and we want to see it go. We have our science already starting to be planned. So from our standpoint, we think JWST is going to be great. And we look forward to WFIRST. So we're going to keep looking at proof of concepts and simulations and testing technologies and that kind of thing. So we love it to go. And we think it'll be a tremendous capability. So
okay. Well, there you go. At least WFIRST is not, I was worried about it, but I guess it's still limping along.
We're going to keep pushing for it.
In the funding area. Okay. Well, let's move on to some of the science highlights that you found interesting while you were there.
Right.
Now you were there from Monday to Wednesday, right? Or did you?
Yeah, but I know what was going on today too. It was mostly in the morning. There was some stuff in the afternoon.
Yeah.
I would say, there's always education stuff, but that's often on the weekend. It's often on Saturday and Sunday. So there's a lot
They
of
do workshops,
workshops and things like that. But I would say that at least two of the big topics were tests and results from tests and the Sloan Digital Sky Survey. So for tests, which we could start with, so TESS is the Transiting Exoplanet Survey
Satellite.
They have a little different approach than Kepler, but because they look at almost the whole sky. So they were talking about, how that works, that they do these strips on the sky, and what they also were talking about what they would do. They have to think about an extended mission now because you have to plan for it, but that wouldn't start for a couple of years. anyway, they did talk about what kind of results they were getting. And they have found some, I guess you would call them Earth-sized planets. A couple of them might be maybe habitable. They found smaller planets than hot Jupiters, very close to their parent star. But the other thing they were showcasing as well is that they've been finding distant supernovae, which was not really the intent. But this is Kepler has found, stars that change in weird ways, that change because, in fact, that's what those telescopes do, is they look for changes. And the idea is they're mostly looking for changes that are caused by a planet going in front of its parent star. But there are stars that change and other stuff that pops off. And so TESS actually did a very nice press release and had several papers about the supernovae they had found, very faint ones, but they had found them. And they were also talking about the fact that the data becomes publicly available, and a lot of people can look at the data and browse through it and find phenomena as well. The thing about the way that TESS works is that Kepler, which was staring, had to come around and stare again, but Kepler is doing these strips. So they can look at faster period things, and because they resample an area more often, they can actually overlay so you measure all the stars in the field and you overlay it's called the photometry. So you overlay the measurements, and if you do that and you get a straight line with some noise, you say, okay, it's not varying. But they were able to find a number of planets as well as these supernova that they found.
Okay, now I have this image that you sent, SN 1539, up, and what we're looking at, folks, is the things labeled 1, 2, 3, and 4. That is the strip of detectors, the 4 cameras with 4 detectors each, in a big long strip that TESS uses to look at one sector.
So that's an example of a strip, and that had been reobserved. So, for example, actually, Beta Pic is in there, but and there are other objects. You can see there's this small Magellanic Cloud and a couple of globular clusters and stuff like that. What they actually did find was they found a couple of supernovae in this field, and they also found away from, not in the large and small Magellanic Cloud, but in some of the other fields, which are, all those stars are actually in our galaxy. They found a couple that seemed to be candidates for planets.
Look at all those stars, Carol. That's a lot.
I know,
of stars.
it's like a lot. It's a lot. So that's why you need to repeat the observations and compare them over time. And also that's why these telescopes are great for citizen science, because you need a lot of people looking at this data to see if you can find some of the subtle changes. So, for example, I can talk to one. It says one of the new planets, third new planet with longest orbit yet, HD 21749b, orbits a bright nearby dwarf star. About
what are you looking at right now?
I'm looking at the press release.
Oh, okay.
Which the AAS puts out based on. So that one is it goes around in 36 days, which is long compared to a lot of the other ones, because the long period stuff you can't really see, right? Because it has, but if you're trying to observe something that goes around in 5 years, like, some of the outer planets, and your mission has only been in orbit a couple of months, you're not going to find something.
Well, that's been the complaint.
To be repeat. So that's the point. That's why having a long mission is helpful. So this is a lot of why these really short period planets are found is because that's all they can find.
That's right.
So they were saying that this quote unquote long period, because it's 36 days.
Yeah, for TESS it is.
Some of the other ones. So the one I was talking about was Pi Mensa B, which is called a super Earth. So it's a couple times the size of the Earth, and it goes around in 11 hours. So it's like racing around. It probably is mostly rocky and has no atmosphere.
Now, this is one of the candidates that TESS has found, right?
Yeah, both of those are.
So the big complaint that I always hear about TESS, and I don't disagree with it. I think it's a valid one, although I think the way TESS is doing it is also good, is that there's not looking at, it's only looking for these sectors for 2 months, but because that's the orbit that it's in around the Earth, and then it moves on to another sector. So it's got a compromise between, looking at a sector of sky for a long time versus looking at the whole sky. And so the thinking is, if you saw all those stars in there, folks, that's a lot of stars. So a lot of data, a lot of stars. Yeah. So getting 2 months worth of light curves may not get you, like Carol said, the 5-year or the 10-year orbits, but you're going to get something, and probably the high frequency or the high close-in exoplanets. But that's still worth doing.
It is, but remember, they will have we build these telescopes to be in orbit for a certain period of time, but TESS is not limited to its nominal period. So they talked about, George Ricker, the PI, talked about their plans for the extended mission. And in fact, I was part of the proposal process for TESS. And we planned all along. We addressed that in the proposal. What are we going to do if we get an extended mission? So the thing is, it'll have a certain lifetime that NASA has agreed to. Then there's a review. And if they have great results and the spacecraft is healthy and there's money available, they'll extend it.
Right.
And so it won't be limited to a couple months.
But that is one thing that is going to be affected by the government shutdown. TESS isn't affected, but the planning for the extended mission is affected because there's nobody. Well, that's what I read anyway.
Well, somewhat, because the Goddard and the Ames people. But let me tell you, the MIT people are moving right ahead.
Yeah, they're not waiting around for no government.
So it's like fill in this blank here. So they have their sketch of what they want to do. We had to propose for it years ago. So they've had a sketch.
That's true, I guess.
And we do the archive. We have the raw data and the process data. So, and that will continue. So data will come down on us. So really it's the pipeline processing, which could be done by somebody else, but it's been done by Ames. And of course the spacecraft operations, but it's going to operate like it does. So planning for extended mission might be pushed out a little bit, but the MIT people are not going to wait around for their colleagues.
Yeah, and you've got MIT working with TESS, you've got APL working on New Horizons, you've got JPL working on I think they're doing OSIRIS-REx. So that's the advantage of having these other non-NASA entities operate these missions, and the Institute operating Hubble, things like that. So, all right, well, what else do you want to talk about, Carol? You got any more news?
I just wanted to mention, it says already more than 1 million TESS images have been downloaded to the archive, and that was just in the early days. And so that's why they were able to find the reason they were excited, actually as excited about the planets as they were the supernovae, is because TESS is able to find the supernova as they're rising. Usually the classic thing is the supernova is found after it's gone off and then everybody wants to observe it. But TESS isn't particularly looking for supernova, but if there is one, it can see from scan to scan something getting brighter.
Yeah, it's all about serendipity.
Wow. So TESS is one of the few observatories that can actually do that. And that's very exciting. So we're looking at planets near us and supernovae
far away. Were the supernovae in our galaxy, or were they in another galaxy?
They're further away. They're like I thought one of them was actually maybe in the SMC.
Okay. All right. So they're outside the galaxy.
Or pretty farther away. Cool. Okay. In other news. So the other thing is that the Sloan Digital Sky Survey The news about, so the Sloan Digital Sky Survey, it was a survey that was done by imaging from the ground, more wide field, lower resolution than people are used to on Hubble or Chandra or Spitzer, because they very wide field. But the Sloan has produced a huge amount of data that was analyzed by scientists. It also spawned essentially Zooniverse, the citizen science effort. They have so much data, and actually, part of the news is that some of that data is coming to MAST, the archive at Space
I didn't
Telescope.
know that. That's good. That's good.
And what's being released now, so the images were analyzed, and the idea was, at least for the galaxy surveys, they were analyzing the morphology of galaxies, what shapes they are, and then doing follow-up observations to see how far away those galaxies are, so that you can and in fact, Hubble contributed to that. The Galaxy Zoo Hubble then followed up and looked at images in certain fields to see how the morphologies of the relatively nearby stuff that was sampled by Sloan, looked at by the scientists and also by the citizen scientists, how that morphology changes as you look back in time. Like, when did spiral galaxies become spiral galaxies? Were they blobs and then when was that? So that's the idea. Also looking at mergers. So the Sloan has been amazingly productive scientifically.
Let me just interrupt you with a comment from Launchpad Astronomy, who says that is the Energizer Bunny of sky surveys, the Sloan Digital Sky Survey. It keeps going and going and going.
Absolutely. So, so there's that. There's also the analysis of all the stars. The other thing about it is that, years ago, the fact that they had to deal with so much data, and they were trying to understand how to build the database so that the access could be done. So Alex Zalay, who's at Johns Hopkins, just received an award this morning based on his life works on this. And he talked about the early days, and different organizations, different universities were involved in the Sloan, and they had different responsibilities. And so he was working on the database, and he ended up meeting James Gray from Google.
Oh, wow.
And Gray was a database expert. And so Alex convinced Jim to address this problem. And so he related the story, which all of us know, but probably a lot of you know. But the story goes that the question was asked, why do you care about the astronomical data? And he said, which is what we say all the time.
Who asked that question? Why do you care?
Gray's boss.
Oh.
So why do you want to work on this problem? So because, and his answer, which is what we all say, which we've always said, is because the data is essentially worthless. You can't sell it. It has no economic impact. Nobody's going to die over results that we have. But it's scientifically useful, and it's used for all kinds of stuff. Never mind education and blah, 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 and all that stuff. It represents a tremendous challenge in handling the data and how to search for it and parameterize it and store it, and all the things that are related to big data astronomy has been facing out in the open. Not like NIH or, some of the earth science stuff. We've been out in the open for 30 years on this problem. And so people who are in computer science and databases and machine learning are very interested in it, because they can test all kinds of theories and look at storage requirements and all that. Alex talked about the number of disks. Something like, 3% of their disks have failed, and it's over a ton of hardware that has failed over the lifetime. That's only 3% of the disks they've used. So he talks about how you have to have new technology, new hardware, new software. You have to have new techniques. You have to grapple with how do you get your hands around all of this data that people can use. And you have to have techniques for that, because average astronomer in our office doesn't have that capability. So you have to make that capability available, and how they did that. And it's been tremendous. They were supposed to, I think, in 1992, they were going to have 4 years for the survey and 4 years for the data analysis. And they didn't even get all the data analysis done and the stuff in storage and released to the public until 2008.
Yeah, I
remember. So they were like 8 years late.
And there were these huge 3D maps of galaxies that,
right.
you know, of every
the cosmic web and all that.
That's
so
right.
It's amazing, and it's ongoing. And so now the big idea is there were these big plates that were made from the images and were drilled out, and spectra was taking of certain objects, and now the spectra is coming out. And so they were talking about there are some images. I think I might not have had it there, but there are some images. You know, we talked about the morphology thing. So the idea was that they want to take spectra of a spiral galaxy to see which arm is receding and which arm is coming towards us. All that kind of stuff, which you can't tell from an image. There's spectra of stars, spectra of galaxies, spectra of all kinds of stuff. And that stuff is just coming out.
Okay.
And so it does keep on giving it. It's all going to the archive. People can go in the archive and look for spectra now related to all that imagery. So it's amazing. It's just amazing.
So so Sloan is still taking data. Sloan is still providing spectra.
No, they're processing the data.
They're still processing what they took before.
Yeah.
Okay, for those of you who don't, let me just back up a little bit. Sloan is a ground-based observatory located in New Mexico on Apache Point, not too far away from the old National Solar Observatory. And it's a humble little building where they do some really big things. They take the spectra of all of these galaxies so they can get redshift measurements from them, and then they put together these 3D maps. And they've done it for everywhere that they could see over that period of time from the mid-90s until whenever they stopped, and now they're still, even today, processing this data. Can I ask you a related question then? This is you asked about, you know, the Google people wondering what's the big deal, and we're only just now we're still getting data releases from 10-year-old data, 20-year-old data. What effect do you think this is going to have on upcoming surveys like LSST, because they can't do obviously what Sloan did? LSST is going to take a picture of the entire sky every few days. So,
well, Alex actually addressed that, and he's of course involved in it. Is that, and University of Washington has Sloan. They've been a partner in Sloan as well. And in the intermediate, there was a project called Pan-STARRS, and again, that data is in mass. It was conducted out in Hawaii, but Pan-STARRS, which is looking for transient, mostly explosive stuff, not planets, but all that data is being handled and it's available to the public. And so this whole group that has this experience, this consortium, is working on LSST, on all the algorithms, how the searches are going to be done, how the data is going to be stored. So I'm not particularly worried about it, because they've been working on this for 20 years. I've gone to many of their meetings, and it came out of that. So that data will be handled. The thing that seems to be of biggest concern is, how is this stuff going to be sustained in the future? These are gold mines of data that will give back for years. And right now there are people who are worried about, you know, the data's coming to the Space Telescope, we're around for a while. You need some place to curate this stuff for 30 years. And you have to have embedded scientists where the data is to help the rest of the community use it. So you know, we started something rolling and we don't have the government commitment to sustain it. So Alex said today, which was, we've known about this problem. I mean, astronomers know about this problem, but Alex said, you need something that is trusted and persistent. And he said, and one organization is the Catholic Church. but they're trusted and they're persistent. They probably will be around, and they probably will have, they will have some funding, and people trust them to a certain extent. So
you don't think about them when you're trying to do data handling.
But the point is well taken. When you think of that, you go, yeah, but they don't have the money or the expertise. So
or the infrastructure,
the trust, infrastructure, long-term commitment, know-how, expertise. So you need all of those things. And so you can think of organizations that have little bits of that expertise, maybe current infrastructure. But the problem, which is, and this is the astronomy is an icon for big data problems, because there are other data sets like Earth science that are even bigger, that have an even bigger problem.
Right.
Medical research, population, census, all this stuff. So there's all these big data problems, and astronomy is kind of like not the prototype, but it's an example of the problems that you're going to have. And if we're having problems, then everybody else is going to have problems, because nobody else has solved it for us. We haven't solved it, and nobody else has solved it.
Okay,
so this idea of free accessibility, persistent accessibility, the correct infrastructure, the tools to use the data, and the embedded expertise, that we need all of that. And we don't need it just for 2 years. We need it for 30 years.
So there you go, folks. If you're looking for a job in astronomy, this is a good way to get into it. Data handling, data management is always going to be a huge problem in astronomy, and they desperately need people who can work on that. Okay.
And also, if you happen to be a successful business person and you're going to have money for another 30 years, give us a call.
Yeah. I'm noticing a trend in science now where these billionaires are being asked for lots of stuff.
Some of them are really interested.
Remember SETI got the Allen array for looking for SETI stuff.
Exactly.
And if you're a billionaire listening to this, you might want to talk to the Sloan guys and maybe help them out with some data storage infrastructure. Okay, so Tess had some announcements, some good announcements. They presented some things. Sloan, they had a good session. What else stood out for you at the meeting, Carol?
Well, we're going to talk about the image that's behind you, M33. So M33 is one of the Hubble large surveys that took many, many pointings, and they did about. This galaxy is much smaller than M31 Andromeda. So I think it has like 150, 160 pointings, whereas in M31 they did 40% of the galaxy with 440 pointings. So it is a much smaller galaxy, but it's part of our local group. The three main galaxies are M31, our galaxy, and M33. And so we just released the M33 data, which covers the inner part. There's a whole extended part which wasn't covered by Hubble.
I've got that image up now, so maybe describe what we're looking at with the little squares.
So it's a spiral galaxy. What's interesting about it is that, well, it kind of goes hand in hand with the Andromeda study, is the group that is studying it. They've learned a lot about star formation and star clusters and the persistence of dust in these galaxies. M33 is tilted more towards us, not quite face on, but it's like 45 degrees or something. So it's easier to see the whole galaxy and see through the whole galaxy. Sit down. Sorry, my little friend is getting itchy.
It's probably getting
anyway, I've worked on M33 and found we have a catalog of clusters from a long time ago. But anyway, they're going to catalog it, and the recent results, since this data was just obtained and is just starting to be analyzed, is that this galaxy, which is in our local group, actually has had more star formation in the recent in galactic terms than M31, which is really interesting. So for some reason, it fired up and has a lot of star formation that did not happen in M31. So that is going to be looked at much more carefully. But these surveys are important because these galaxies are right up in front of us, and we can't hope to understand anything about galaxies that are very far away if we can't figure out what's going on in these galaxies.
And this
so
is
that's why it's so important.
Yes, and this is a super high resolution image.
Super
Each one of those little squares is a pointing of Hubble, isn't it?
Yes.
And it was mosaic together.
Yes. And the other interesting thing about it is the Milky Way in M31 is the biggest and the most extreme as far as the amount of chemical elements in it. So it is what astronomers call metal rich. So it has
we've talked about
higher abundance, and then Milky Way, and then the Large Magellanic Cloud, and then the Small Magellanic Cloud, and M33 fits right in between. So it's a transition. So in our local group, we have this whole range. And it's important to understand, how does all this stuff work in these different environments, and how does it work in galaxies that have different morphology? The question we sometimes like to ask is, does a cluster of stars know what galaxy it's in? Now, it's a funny question, but the type of galaxy may actually have something to do with the type of star clusters and the H2 regions and all that are, and the spiral arms that are formed. So it's a beautiful transition galaxy, and the group was never allocated time to do it until recently. They had proposed to do all of them, but they just got the M33 data. So we had the two mosaics up at the meeting in the hallway. We had the big M31 mosaic and the big M33 mosaic.
Yeah, the M31 mosaic was done a few years ago, and this one
we still have it. So we keep bringing it back because it's a favorite.
So this, how many? So the you're talking about the FAT survey. That was like 500 pointings of Hubble.
440.
440. How much was this one?
About 160.
Okay, so a little bit fewer than 200. And so what's inset in here are little squares, and they're blown up here off onto the right side. So there's that blue thing that's outlined in the upper left of the galaxy of the mosaic that turns out to be NGC 604. And then
it's a beautiful image of 604. It is just stunning. It's just amazing. And then my favorites, globular clusters, a bunch of globular clusters. There are background galaxies. As I said, the tilt is such that you can see through it. And then also the foreground stars, just for people to be able to orient themselves with what all the objects are in this galaxy.
So globular clusters are groupings of stars that are very old. These stars are very old, right, Carol?
Mostly, although in the study that we did, we found that there were star clusters that were intermediate age that had they don't have as many stars in them, but they are spherical in shape. And that is also true in the Large Magellanic Cloud.
So going back to your comment about, does a cluster know what kind of galaxy is in? It's in would an older galaxy have more star clusters because the stars are older, or and less star formation? Or
it depends on the gas and dust content. Like elliptical galaxies, for whatever reason, mostly have run out of their gas and dust. So they have old star clusters because they used it up. Whereas spiral galaxies, for whatever reason, have continuing star formation in them. And so there are the original, in general, I'm making very broad statements here. In general, the classic globular clusters have 10,000 to 1 million stars in them, and they in general are old. And in our galaxy, that's true. And then we have things that are clusters that don't have as many, several hundred. In LMC, a little bit the SMC, and in M33, there are clusters that are intermediate in the age that have lots and lots, hundreds and hundreds, and maybe 1,000 members, or maybe even 10,000 members. But they're not old. They might be 1 billion years old or 500 million years old, something like that. So it's curious, like, why is that?
Yeah, and Hans Milling is commenting that background galaxy has some serious redshift unless it is false colors.
No, it's dust.
It's dust in the way. So good question, Hans.
It's dust.
Yeah.
So what we're seeing is the really dark stuff is dust, but there's also dust all across it. And in fact, for M31, the map hasn't been done for M33 yet, but for M31, they showed how they derived by knowing that when you have many filters, when you take the images with many filters, you can figure out what kind of stars you're looking at. And they did a dust map. It's impressive because when you look at M31, you don't realize how much dust is there, and they completely mapped it. So they're going to do that here. And there's a lot more dust there. We actually had a discussion about the color. We only have a few filters, so we have to use red, blue, and green. But it's mostly red, not because everything's old, but because there's also a lot of dust in the way. In the sense, there's more dust in the center than there is in the outlying parts.
Now, one of the surprises about this image, I think, if I read my press releases right, was that there's a higher than expected amount of star formation in this galaxy.
That's what I was saying.
Yeah.
Is that the star formation is more recent.
Okay.
Than in M31. So higher, that phrase means that it's more recent. You would have expected it to be the same epoch as M31, and it's not. It's more recent.
Yeah.
We don't know why.
Can we talk a little bit about this false color business? I hear this a lot. This is something that people don't really do anymore in astronomical images. False colors generally were used as when detectors were of a shorter bit depth, and they were in wavelengths that we really didn't have the kinds of colors. They would bring out details in certain color tables using a certain color than if you didn't.
We do that.
Huh?
We do that.
I know, but when nowadays you've got filters in a certain color.
I know, but
and you apply that color to that filter, it's not false anymore. It's the actual color.
Well, it's not the actual color. If you apply a blue filter to ultraviolet, we can't see ultraviolet.
Okay, fine. So yes,
so if we try to color, if you want us to show the ultraviolet, you won't be able to see it.
All right, I stand corrected on that. But you're right. Outside the visible range.
Okay. No.
You're right.
Let me. Okay. So it's called the thermal color scheme. So you go from blue to red, from the ultraviolet or even the X-ray, right, to the red, the infrared. You can't see those. We can only see a little bit of that. But what we tend to do is we do this thermal map thing where we map the bluest colors to the ultraviolet and the blue, and the greenish ones to the visible that we see, and the reddish ones to the near infrared and the infrared. Depends on what filters you have. I mean, we put it that way because it makes people feel comfortable,
right? Because
that's what they do. But when you have emission lines, you end up, it makes no sense. H alpha is red, but it's so red we can't see it. So we usually use a red
color
tint to do that. Oxygen, some of the oxygen lines are in the yellow, so we use yellow. So if you have emission lines, and in fact, we do have a rendition of 604, the H2 region, which is quite colorful. And if you Google it, you will see all kinds of because there's a lot of hydrogen in it. So some people have made it more red because that's a lot of hydrogen. In other cases, people have colored it differently because they've enhanced the oxygen emission, but those are in very specific energies. What the thermal map we use it because stars emit in all the filters. So we just simply assign blue, yellow, green, red, in that order because it's what people are used for. None of this is what it looks like. If you went out there in space and looked at M33, it looked gray because your eye cannot see those wavelengths.
Okay, I guess I stand corrected, but I do agree. I know in wavelength ranges outside of our visible eyes, we have to apply colors just so we can make sense of it. I guess I was talking more about the ones that are in the filter wheels of wavelengths that we can see. But you're right. The wide field camera 3 is mostly infrared, and it's in the 1 micron or so range, and so we can't see that. So
I did want to talk about one, just to go back for one second.
Sure.
Is that there were a couple of images that I had. One was called manga star library, and the other was called Master Spectra. It was just to show the concept of the Magna star library is like the archive of the spectra that Sloan is producing. So that's a evocative poster about that, if you wanted to show that.
Okay, it's up now.
So that was an illustration to show the idea that it's a big library and it has spectra of all the objects that Sloan looked at. And the master spectra sample is one that has known objects and what the spectra look like when they were observed with the Sloan detectors. So those kind of help explain this idea of the library of spectra as opposed to the library of images that Sloan has produced. Okay. So I just wanted people to see that because that's the concept.
Yeah, that's really cool. And then you have another one right next to a MA star spectra. Is that right? Is that related to this? Or
MA star is the H2 diagram in color.
Okay.
It's just showing all the types of stars for which the spectra have been observed, and then you can put them in the temperature and luminosity diagram to show all the different kinds of stars that were observed. So there are galaxies observed, and then there were lots of stars observed by Sloan. And that's the representation. Okay,
we only have 5 minutes, and I want to ask you about WFC3 on Hubble. Alert came out Tuesday, I guess, on this is the premier camera on the Hubble Space Telescope. All the images that the Triangulum Galaxy we just looked at, all of it were products of the Advanced Camera for Surveys and the WFC3.
Yes.
What's going on? Everything okay?
So we got an alert, I think, on just hold on. Yeah.
It was like Tuesday, I think.
Okay. Hold.
He's only got. Just tell him he's only got 5 minutes. Oh, little guy. All right. So, a couple things. Deep astronomy. Is there a color assigned to each filter? That's from Larry Keese. Well, like Carol said, I guess they just do it with what looks good to us. So there's no real standard to assigning colors, and there's no real color tables, but there are ones that make more sense.
It's like a child. She's been taken care of by somebody else, and this is my first day with her back, and so she's like,
you got to give pay attention to me. You got to give her some time. Okay. Well, we won't tell her 5 minutes, 3 minutes.
Yeah. So the idea was that we got an alert that there was something going on with Whitefield Camera 3. Very often these alerts are because they're what's called a single event upset, and that's caused by charged particles. Their telescopes in space get charged particles that hit them all the time, penetrate the electronics, sometimes upset things. So they're taking a look to see if that's what it is. Initially, it looked like that was not what it was, and that maybe there's something happening to one of the low voltage power supplies for the one side of the camera. And so all of these electronics are redundant. So what usually happens is you do the safe thing, is that you don't use the instrument, and you go ahead and do science with the other instruments, and then you look at the data that you have, and then you do some tests. And in principle, the way these things work is when you have a problem like this, you switch to the redundant electronics. But they don't do that, frivolously, and they didn't want to run the instrument without understanding it. So you need to look at all the data that came down, what happened exactly when you had a problem. They ponder that. It's a little bit awkward because we got to bring people in who. Most of our guys, the scientists and the engineers at our place, can address that, but we do need to talk to NASA about it. But some of the essential personnel are able to work on it, and they just have to figure out what it is, because you don't want to just, it's like when you have a problem with your car, you think you know what it is, but I ran out of fuel. Well, no, it was actually your fuel pump, and you could do more damage to your car if you don't stop and take a look. I actually recently had a problem like that on my car, and it was something where my car quit, but then it was really intermittent. And then finally I took it in, and they were like, man, you just made it, because you were going to have a really expensive trip here if you didn't bring it, if it had happened one more time. So you don't want to just frivolously use the instrument until you actually thoroughly understand what's wrong and how you're going to fix it. So it'll be good. I think it'll be recovered. It'll be back.
Okay.
We're just taking a deep breath.
But it's off right now, and you're
as far as I know, maybe they may be collecting data from it, just to see what the electronics are doing. I do want. This is my own personal opinion, people. This is not anything official, but I was very disappointed at the Nature article because Nature, the stuff that I saw in Nature is not anything that we or NASA put out. And Nature, I thought, was a respected journal, and I'm very upset that the journalists said some things in that article which just are unfounded.
Right. And
Hubble is like quit and hamstrung by the furlough. Not true.
I've noticed that about Nature. It's not been. You're right about.
It's really sachet, and I'm sorry, but that's not responsible journalism. National Enquirer maybe, but Nature as a journal, no. Yeah, that's not correct.
Okay.
So I'm a little. That's my own personal opinion. It's nothing official, but I was a little grumpy about it. So,
yeah. Well, anyway. Good. I've noticed that too about Nature. So basically, the summary is Wide Field Camera 3 is down right now. They're checking out. They're thinking about what's going on.
What's wrong with it?
But they've got backup electronics.
We're doing other stuff. So
yeah, there's still the other.
And then when it comes back, we just reschedule it. So we'll lose some observations, but usually we can, we have so many observations, we can shift things around. So that takes a little bit of time to redo the schedule. Okay. But then we continue getting data, people do science, and I'm sure it'll be back.
Okay, cool. Well, thanks, Carol, for the update. I was a little worried. I'm glad it's good to go. Nick Belaine, I have noticed you. He writes a comment. Tony, notice me. There, I have noticed him. Okay. And then somebody else is like, calm down, man. So anyway, cool. All right. So anyway, we're going to have to stop it here because we're out of time. Yeah. Carol and I have been talking about some changes coming up in 2019. We are probably going to scale back the Astro Coffee Hangouts to 1 per month. And on the other Thursday, still same Thursday, still same time, but it's going to be the 4th Thursday of every month. And Astro Coffee usually happens on the 2nd and the 4th of every month. On the 2nd Thursday, Carol and I are going to record a podcast together. And it's going to be on the Deep Astronomy podcast that you guys are already subscribed to, aren't you? If you're not, it's on iTunes, or just go to anchor.fm/deep astronomy, subscribe to it there. So that's going to happen. So the next Astro Coffee Hangout will be February 28th. Okay. So that's going to be the next Astro Coffee. However, on the 14th, Carol and I are going to record our first podcast. So look for some changes there in 2019 on these Hangouts. And I guess that is it. I want to thank all of you guys for watching. And as always, keep looking up.
Looking up.